All right, so in the previous video, we left off talking about saturation. So when your shirt is completely saturated with water because you just ran out in the rain, it can take no more water. It is fully saturated. However, if it's only sprayed with a little bit of water, maybe we would say it is unsaturated because it could take more water. And if it is super saturated, then it has way more water than what it can hold. In the case of chemistry, saturation, you could talk about Coca-Cola or soft drinks in general. Whenever you crack the top of a Coke, you hear the hiss from the CO2 escaping. It does that. It escapes because the solution, the Coke, is super saturated. So just like everything else, it wants to reach a state of equilibrium so that it would become saturated once you leave it out and it becomes flat. But really, it would still probably be super saturated because of the amount of sugar that's dissolved in that Coke. That's probably why they put so much acid in those things to help dissolve all that sugar. A ton of sugar. But in the case of lipids, so let's translate this idea of saturation to lipids. So here's the very, very bad drawing of a triglyceride. Here's your glycerol head and your 3 fatty acid tails. So these fatty acid tails, there are no open bonds. So they have as many hydrogens as they can hold. So we would consider these saturated. All right, so let's take a look at what it means to be saturated. These fatty acids are saturated with hydrogen atoms. The molecule has no open bonds to put any more hydrogen on. There are no carbon-carbon double or triple bonds in these chains. Saturated fats are solids at room temp, and they usually are associated with animals. Saturated fats contribute to coronary artery disease. So when you take out a stick of butter, it is a solid at room temp, so it is chock full of saturated fats, whereas if you take oil like canola oil here, it is a liquid. So it should have quite a few more unsaturated fats in it. So let's take a look at the structure to help it try to make sense of all this. So we say that this is saturated because it contains as many hydrogens as possible. But what happens if we say remove a hydrogen? What then will happen? Well, what could happen remember, carbon wants to form 4 bonds, so it has 1 bond up here at the top. Oops. So here's a carbon. It has 1 bond at the top. It's going to form a bond with this carbon, but in this case, it forms a double bond, which is represented by 2 lines. So we have a double bond. And then, so a hydrogen will then fill in this place here. So what actually happens is that this fatty acid tail begins to change shape. It actually begins to bend. So our CH3 is off to the side just a little bit. All right, so it completely, it changes the structure of the fatty acid chain. So let's say if this happens over here, if energy is applied, and we form a bond, a double bond between this carbon here, we form a double bond there. We have a CH3 with a hydrogen here. All right, so to get a better idea, let's change this CH3 to show us what's going to happen. All right, so now we continue our chain. Our chain's longer. So look how the structure bends. So now we have CH2, CH2, CH3, CH2, H, 2 and CH, 3. Now, I don't have a ton of room to continue on, but I guess if we take a look back and zoom out a little bit, you're going to notice this bend is going to take shape. So a good illustration is your hand. So we said earlier that if you do your hand like this and point your index finger out, that your hand is the glycerol head. All right, so this is the glycerol head here. It lagged. So then your finger was your fatty acid chain. Well, in this case, we're talking about a triglyceride, like what I just drew. So we're going to have 3 fingers, okay? So this was our initial shape. Our fatty acid chains were straight, stacked together, fully saturated. So this is a saturated fat. And now, once we introduced double bonds, what happened then? Our fatty acid tails bent. So here is your unsaturated fat. Saturated, unsaturated. So if you think about it, solid versus liquid, why is a saturated fat a solid at room temp? Which one is easier to stack? The saturated fats. All right? You cannot stack the unsaturated fat with these bent tails. Remember, the tails are bent because we introduced double bonds in between the carbons. All right, so here's your illustration for an unsaturated fat. So maybe one claim that we can make about saturated fats in their contribution to coronary artery disease, basically causing potentially a heart attack, is their ability to stack on top of each other and accumulate inside of your arteries and block your blood pathway, whereas unsaturated fats may not. So unsaturated fats have fatty acid chains that contain some carbon-carbon double or triple bonds that could be broken to add more hydrogen to the fatty acid. Saturated fats tend to be liquids. Nope, that's a typo. Unsaturated fats, make sure you change that, tend to be liquids at room temp, and they usually are associated with plants. So like I said, canola oil, all right, comes from plants. Sunflower oil, peanut oil, unsaturated fats are typically viewed as a healthy part of the diet. Then we move on to polyunsaturated fats. These fats have many double or triple bonds in their fatty acid chains. So rather than taking the time to draw polyunsaturated fats, we can just simply Google it. All right, so here we have 0 double bonds, and we have a saturated fatty acid. Every carbon has the correct number of bonds, hydrogen bonds, and is fully saturated with hydrogens. All right, here we have 1 double bond. So we have a monounsaturated fatty acid. So it's unsaturated because we're missing a hydrogen, and mono because it only has 1 double bond. Do you see how bent that tail is? All right, now we have 2 or more double bonds, and then we have a polyunsaturated fat. So we have many of these double bonds, and it is unsaturated because everywhere there's a double bond, we could use more hydrogens there. So that's the difference between polyunsaturated and monounsaturated. Now we have what are called hydrogenated or trans fats. These are the ones that you do not want in your diet. They are not good for you. These are oils turned solid fats by adding hydrogen and by breaking the double or triple bonds in the fatty acids. This was done in the past to change the texture, stability, and shelf life of fats. Trans fats were common in processed foods. They have been shown to increase low-density lipoprotein cholesterol levels and to contribute to coronary artery disease. So the LDLs, if you ever have a physical, LDLs you want to be low. HDLs, high-density lipoproteins, basically pick up junk in your bloodstream and move it along. But low-density lipoproteins just get stuck and contribute to coronary artery disease. So trans fats were artificially, hydrogen was infused to cause oils to turn into solid fats. It's a marketing thing, to try to get the food to last longer. Your processed food, like maybe say your chicken nuggets. Maybe we want some trans fats in there to make them last longer, or possibly still taste good, but then last longer. But they're not good for you. Your body does not break them down. Phospholipids. So phospholipids are highly significant when talking about cells. If you remember, what is the cell membrane made of? Phospholipid bilayer. So we have two layers of phospholipids. See right here. Phospholipid bilayers are important for building the cell and organelle membranes. So these molecules replace a single fatty acid chain from a triglyceride with a single phosphate ion. The phosphate portion of the molecule is hydrophilic because of the charge on the phosphate ions. The remaining fatty acid chains are hydrophobic. So why are they hydrophobic? Because they're nonpolar. They're fatty acids. Why is phosphate hydrophilic? Because it is polar, it attracts to water, so it's hydrophilic. They are mostly composed of long chains of carbons that are also bonded to hydrogens. They are neutral and are not attracted to water. All right, talking about fatty acid chains. All right, so here's a key word for you, amphipathic. What does amphipathic mean? Phospholipids are said to be amphipathic since they have both polar and nonpolar sides. Phospholipid bilayers are a good example. So if not for the ability to be amphipathic, your cells would not survive the way that they do. Okay, so here is your diagram for a cell membrane. Here's the water on the outside. Here's the interior of the cell. Here's the inside layer and the outside layer. And notice the orientation. All the tails are pointed inward. Why is that? Why are they pointed inward? Because water is out here and they're hydrophobic. They're pushed away from water because they're nonpolar. And then the phosphate heads are hydrophilic. So then they are attracted to the water, and the water actually sticks to them, and they stick to the water, and they form this nice relationship, and the water actually helps to keep the cell membrane stable. All right. So if that didn't make sense, go back and replay that because that's very significant. Being amphipathic and knowing which end is attracted to water and which end repels water. So when we talk about diffusion and cell-to-cell communication, that's going to be very, very important. Okay, so the last lipid that we're going to talk about are steroids. So a steroid is a commonly used phrase. You've all heard of steroids, or you've maybe gone to the doctor and gotten a steroid shot to help you fight through if you've had pneumonia or whatever. It kind of ramps up your body's systems to help you fight through it. So a steroid is a lipid composed of 4 carbon rings. Common steroids found in the body include testosterone, estrogen, progesterone, and cholesterol. I bet you didn't know cholesterol was a hormone. What makes them different from each other are the attached functional groups. All right, so highlight that. If you're going through your notes and highlighting, highlight that. Structure equals function. And so this is what's actually going to be different. These functional groups help determine the function of the steroid. Most of the steroids are built from cholesterol. Steroids function in the body as cell signals or hormones. They allow cells to communicate with each other. Due to their lipid nonpolar nature, they can penetrate the cell membrane and bind to intracellular receptors, which is something we're going to talk more about when we get into cell communication. Time's out. See you next time.